This is the method I taught my A students on how to always nail acids and bases. We're going to start with this question, and you'll see how I apply the method in the more challenging parts of the question paper. So, question 7 says, the conductivity of 3 acid solutions, A, B, and C, are investigated at the same temperature, and they show us these 3 solutions below. The brightness of the bulb in the apparatus shown below is used as a measure of the conductivity of the solutions above. So we see the diagram there with copper electrodes and an acid, right? So now that they've given us that, the questions then come and say, the acid solutions are electrolytes. 7.1.1, define the term electrolyte. So very simple, very easy. An electrolyte is a substance whose aqueous solution contains ions. Nothing crazy, nothing hectic there. Let's jump further on to get to some nice calculations. 7.1.2, in which solution A or B will the bulb be brighter? Give a reason for your answer. So when looking at 7.1.2, let's first consider what A and B have, right? So we can see there A is 0.1 moles per decimeter cubed of H2SO4, B is 0.1 moles per decimeter cubed of HNO3. Those are both strong acids, as you should know your strong acids. So what can we use to differentiate them? One thing I want you guys to see very easily is now when we're talking about polyprotic versus monoprotic acids. We can see there that HNO3, nitric acid, is a monoprotic acid, whereas sulfuric acid, H2SO4, is a polyprotic or diprotic acid. Diprotic acids being able to give off more than one hydrogen whenever they react, and specifically sulfuric acid gives off 2, right? So whenever they both react, for every 1 hydrogen nitric acid gives off, sulfuric acid will give off 2 hydrogens, meaning there will be more ions in solution, and in that case there, it'll make sulfuric acid a lot more conductive than nitric acid. So in that case there, for 7.1.2, the answer will then be as follows. Which one will make the bulb be brighter? That's going to be definitely A, right? The sulfuric acid. Give a reason for your answer by referring to the types of acid. And you can simply say there that H2SO4 is a diprotic acid. Perfect, easy, nothing too hectic. 7.1.3. 7.1.3 then says, in which solution B or C will the bulb be brighter? Give a reason for the answer by referring to the types of acid. So we go back, we look at B and we look at C. B is still nitric acid, 0.1 moles per decimeter cubed. And then C is going to be 0.1 moles per decimeter cubed of acetic acid. Now what you need to know there again, nitric acid, strong acid. Acetic acid, weak acid. Remember, your strong acids will ionize completely, where your weak acids will only ionize partially. So the ones that ionize completely will have more ions in solution and therefore be a more conductive solution. And that's your answer for 7.1.3. So in this case here, your answer will be B, your nitric acid, HNO3. And the reason is going to be HNO3 is a strong acid. It will ionize completely. Awesome, nothing crazy. Let's do some calculations. 7.2 will be as follows. It says there, a hydrochloric acid solution, HCl, is standardized by titrating it against 25 cubic centimeters of a 0.04 mole per decimeter cubed sodium carbonate solution, Na2CO3. At the endpoint, it's found that 19.5 cubic centimeters of HCl has reacted. The balanced equation for the reaction is as follows, and we're given there sodium carbonate plus hydrochloric acid, giving us sodium chloride plus carbon dioxide plus water. Calculate the concentration of the HCl. So in this case here, we need to then try and figure out the concentration of the HCl, where we are given the volume and concentration of our sodium carbonate, in that case there, and we are given the volume of the HCl that has reacted. So this is quite an easy one. We can use a titration calculation there. So using our titration calculation, we can simply go and put Na over Nb is CaVa divided by Cb VB. What we need to do now is go substitute our values in, right? So for the number of moles, we can simply just use the mole ratio there, 2 and 1. So 2 being for our acid, 1 being for our base. So we're going to have 2 divided by 1. The concentration of the acid is what I'm trying to solve, so I'll leave that there. Volume of my acid I was given, that's that 19.5. Concentration of my base is going to be the 0,04. And the volume of my base is 25 cubic centimeters. Now, some of you guys might be wondering right now, why did I not convert my volumes from cubic centimeters to cubic decimeters? And that's because when I do the conversion from cubic centimeters to cubic decimeters, I'd have to simply just divide that by 1,000 and divide that by 1,000. But notice how if I divide the top and bottom by 1,000, I really didn't do much. So you can, in this case, leave it out. Don't always do that. It's always easier to convert, but in this case, mathematically, it doesn't make much of a difference. All I need to do now is make Ca the subject of my formula, and then I've got Ca is equal to 2 times 0,04 times 25 divided by 19,5. Plug that into my calculator. And you should find that you'll get an answer of 0,10 moles per decimeter cubed. Awesome, that's the concentration of the hydrochloric acid that we're dealing with in this particular problem. Great, let's move on to the next question, 7.2.2. 7.2.2 then says, suppose a few drops of water were present in the burette before it was filled with hydrochloric acid. How will the volume of the HCl solution needed to reach the endpoint be affected? Choose from greater than, smaller than, or remains the same. So think about what would that mean. So if you've got water in the burette, when you add your HCl, when you add water to HCl, what you're doing is you're diluting it, right? Meaning you're going to have less moles per unit volume. So in this case, it means you now need to add more of that solution to do a titration to reach the same number of moles. So what I will need is a greater than amount of acid. And the reason is the drops of water will dilute my acid and I will need a greater volume for the same number of moles. Awesome. All right, the next part of the video will then say, a concentrated household product, ChemClean, contains ammonia as its main cleaning agent. To determine the amount of ammonia present in 1 decimeter cubed of ChemClean, the following procedure is then followed. 20 cubic centimeters of ChemClean is added to a 250 cubic centimeter flask. The flask is then filled to the 250 cubic centimeter mark with distilled water. So we can see that they show us exactly what happens in that scenario. The diluted solution is then titrated against the hydrochloric acid solution from the concentration as calculated in question 7.2.1. During the titration, 22 cubic centimeters of the diluted ChemClean solution is neutralized by 18.7 cubic centimeters of the hydrochloric acid solution. The balanced equation for the reaction is shown below. You've got ammonia plus hydrochloric acid giving you ammonium and chloride ions. Calculate the mass of ammonia in 1 decimeter cubed of ChemClean. All right, so this is the method I wanted you guys to really practice. And the method is when doing acids and bases questions, you often have multiple steps to questions that can often leave you a little bit confused and stuck and not sure. So what I often do is I like to call it the roadmap method. So you put out a roadmap of how you're going to solve this problem, and then you basically follow everything through step by step. So to apply my roadmap method, I start off with my end goal. End goal is the mass of ChemClean, right? So to find mass, I know mass is going to be the number of moles times my relative molecular mass. The relative molecular mass I do have, The number of moles, however, to find that, it's the number of moles within the 1 cubic decimeter, right? I need to find the number of moles that are going to exist in my 20 cubic centimeters, right? To find that, I need to know how many moles that I have in my 250 cubic centimeters of the diluted one. It was the same exact amount because all I've done is added water, all right? To find that, I need to then go figure out through the titration process, right, the number of moles of HCl that have reacted. And that I can simply find through the titration calculation that I need to do, which is going to be pretty easy to do in that case there. So let's jump in, because we know that the number of moles of HCl that reacted is going to be equal to the number of moles of NH3 that reacted. So if I can work all of those things and I can work my way back, I can then go figure this out from the information, calculate this, calculate that, get this, and that'll give me the answer of what I'm looking for. And this is what I call the roadmap method. Because once you've done this, it's pretty easy now to not make the mistakes. The challenge with acids and bases is that sometimes people tend to get lost in the maths, forget what they were trying to do the whole time. But if you've drawn your roadmap, you've got a very clear plan from A to Z of how you're going to get there. So let's start applying our roadmap and then see how we can work our answers out. First thing we need to do is find the number of moles of HCl that reacted. We're going to use information given to us here where we've got the volume and the concentration we calculated in a previous question. So step 1, calculate the number of moles of HCl that reacted. So N is equal to C times V. The concentration we worked out previously to be 0.1 moles per decimeter cubed. The volume was given to us just up here as 18.7 cubic centimeters. In this case, I do have to convert, so I have to then divide it by 1,000. So we'll then end up with 18.7 times 10 to the negative 3 cubic decimeters. If you calculate that and put that together, you should then get an answer of 1.87 times 10 to the negative 3 moles of HCl. Now we've done the first part. We can tick that off our list. So this is now done. I need to keep going down my roadmap. The number of moles of HCl that reacted, all right, is 1.87 times 10 to the negative 3. We need to then find the number of moles of ammonia, right, that were in the titration. So we've got this, we've got that. Now that we got the number of moles of HCl, we need to find how many moles of ammonia were in the 250 cubic centimeter solution of ChemClean. So the first thing we have to do there is say, well, we know that we had 1.87 times 10 to the power of negative 3, right? But we have to divide that by 22 because that's how many we had in the 22 cubic centimeter. We want to figure out how many moles would have been in the 250 cubic centimeter. So we're going to multiply that by 250 cubic centimeters, and that will give us the number of moles of ammonia, of NH3, in our 250 cubic centimeter sample. Right? If you take that and you plug that into your calculator, you should get an answer as follows, right? So you'll get 0.021 moles. Okay, now we've got the number of moles of ammonia in the 250 cubic centimeter sample. We can then try and figure out, okay, that was a diluted one. The concentrated one had the same amount because remember, the 250 is this one here. The difference between this 250 here and this 21 here is just that it was diluted. So the number of moles will be exactly the same, right, in that case there. So we can say, well, the number of moles of ammonia in our 250 sample is equal to the number of moles of ammonia in our 20 concentrated sample. So then from there to try and figure out, well, how many moles did we have in the big sample, the 1 decimeter cubed sample? All we have to do there is say, well, okay, from 20 cubic centimeters, it's the number of moles of ammonia in the 1 decimeter cubed, right? It's going to be that 0,021. And in this case, we then divide it by the 20, and then we multiply it by 1,000 because it's 1,000 cubic centimeters in 1 decimeter, right? That should then give you an answer of 1,05 moles. Remember, the question is looking for the mass, not necessarily the grams. So we've gone all the way on our roadmap. We've found this one now. We've even found the number of moles as well that we needed there. Substitute that into the main equation of mass equals moles times molar mass, and then we can find the mass that we've been asked to solve. So just quickly do that as our final step. Mass equals number of moles times molar mass. The number of moles we had up there, which is 1,05. The molar mass of ammonia is going to be 17, which will give us a final answer of 17,85 grams. That is how you apply this roadmap method to acids and bases questions. And you'll find that acids and bases questions become a lot less difficult and daunting and challenging if you apply that method. Thank you guys for following us with this whole process. Let's get our final 3 marks so that we ensure we nail down all of the marks for this particular question, right? 7.2.4 says, will the pH of the solution at the end of the titration be greater than 7, equal to 7, or less than 7? Write down the relevant equation as motivation for the answer. So in this case here, let's think about it, right? We had ammonia mixing with hydrochloric acid. So that's a weak base plus strong acid. That tells you that you're going to have an acidic solution afterwards. That means we will have a pH that's going to be less than 7. Right? So we can easily then already for that question then say, easy, that's going to be less than 7. And they said, write down the relevant equation as a motivation for your answer. So the motivation we can write in there is how, what we'll see in the original equation, we saw there that we produced NH4, right? In that case there, the NH4 comes from our weak base. Remember, a weak base will have a conjugate acid that is fairly strong, which will react again. HCl is a strong acid. The strong acid has a weak conjugate base. The weak conjugate base doesn't react again with water. So HCl's conjugate base is chloride ion. It doesn't react with the water again to change the pH. However, ammonia is a weak base, which is going to then have a strong conjugate acid being ammonium. So when ammonium reacts with water, it will change the pH, and that's the equation they're looking for. So the equation we're going to then put down here is going to be as follows. We're going to have our NH4 plus ammonium in aqueous solution, right? That's going to react with water. Our water will simply just be a liquid, right? That's going to be a reversible reaction. And then when that, our NH4 plus is an acid, it'll donate the H plus. It'll then remain as NH3 in aqueous solution. Plus, we're going to then have H3O plus. And this again reminds you, remember the Arrhenius model of acids and bases says an acid is a substance that will increase the concentration of H3O plus in water. That's how you guys make sure you nail all of your acid and bases questions. Please make sure to follow us, like and share all of our content so that you can pass and your friends can pass and you all end up doing well together. Guys, see you guys next time. Cheers.